Thanks so much, John, and thanks, Yas and Paul, for the invitation, and all of you for coming. So I will present joint work with my PhD student, Wenta Wang, on content moderation. And just to think about how we're thinking about content moderation, let's go back to the beginnings of the century. The beginnings of the century, when you were going to a forum, you would have a human moderator read every single post that is posted, and then they would make a determination whether this post should be removed from the forum or whether it should be kept on the platform. Which is nice because this forum moderator actually had a very good idea about what should be kept on the platform. So this was a very reliable process, but at the same time it's extremely slow because you end up in a situation where you will need to read every single post. So fast forward, if we go to the sheer volume that exists at Facebook or Twitter, you cannot hope that you will have a human reviewer read every single post that is posted on the platform. So what those companies are using is that they're using machine learning and AI in order to make determination about whether the post should be removed or whether it should be kept on the platform in an automated fashion. So this is significantly more responsive, but at the same time, it is prone to errors. And those errors also often come with risks. For example, you may end up violating content on the platform, a content that violates the community standards, or maybe you're going to censor perfectly legitimate content of which you would like to not censor. Now, I will discuss everything with respect to content moderation, but I want to emphasize that everything that I'm discussing is not specific to content moderation only, but it arises in many other settings. For example, if you think about automated claim resolution. For example, Pingan, a company in China, is using AI in order to make insurance claim decisions in an automated fashion. Similarly, if you think about call centers, you remember what happened with Air Canada and the claim that the customer had that ended up meaning that Air Canada needed to reimburse them afterwards. Or there was a recent case where some lawyers used LLMs in order to write their legal briefs, and LLMs ended up hallucinating, and those people were fired and fined. So many of the things that I'm actually discussing are not specific to content moderation, although I'm going to discuss them in the content of content moderation. So what is the setting, essentially? What is the way to try to mitigate the risks that arise because we want to use AI when we have this limited human capacity? Really, in order to understand it, the typical pipeline that we're focusing on is that there is the post arrive, and we need to make an automated decision immediately, a classification decision, of whether we should keep the post on the platform or whether we should remove the post. Subsequently, we also make a decision about whether we're going to send the post for human review. So if the post is sent on human review, it enters a queue. And whenever a human reviewer becomes available, potentially we're going to get one of the posts from the queue and schedule it to the human reviewer. Now, the human reviewers have two roles. On the one hand, they have an enforcement role because they can revert the incorrect classification decision that was made. For example, if a post is left on the platform, but then we realize that it is a post that violates the community standards, the human reviewers are able to actually remove the post. And also they have a labeling role, because they provide label data so that the AI system can make better classification decisions for future posts. So the main question that we're trying to address in this talk and this work is how can we combine the responsiveness from the machine learning with the reliability that comes from human reviewers. And really, we're thinking about settings where we need to rely on AI automation because you cannot hope to send everything to human reviewers when you have a limited human capacity. So this is the high-level agenda, I guess, a high-level question that we're discussing in this talk. So let's just give some Facebook data just so that we are on the same page. Anybody has a guess about how many posts are posted at Facebook every month? Anybody who hasn't seen the talk yet?
Trillion.
A trillion, no, that's really less, something like 60 billion posts per month. This is data from a year ago, but I don't expect that to have been a trillions in a year. How many human reviewers does Facebook employ?
1,000?
It's a little more, it's 15,000. But if you do the math, you will soon realize that in order for to send all the posts to human reviewers, you will need to send 4 million posts per month to human reviewers. If you divide by 30, you will soon realize that actually this is not a number that you can hope to actually send. So, and Facebook is realizing that, and this company is essentially, so this from Facebook community standards. They say that we use automation to help us quickly route the content to reviewers. And the goal is that our review teams focus on the most important cases. And also, the goal of AI is to detect repeated violations and obviously identify graphic or extreme content. But for the posts that have higher degree of ambiguity, complexity, or nuance, we would like to actually use human reviewers. And as I said before, there is not only the enforcement role, there's a labeling role from Facebook community standards. Again, the AI, the humans are important so that they can simultaneously train and refine our technology. So this human technology feedback loop is vital to keep the systems current. So these are from Facebook community standards. So let me discuss what is a high-level pipeline before discussing formally our results. So when a post arrives, we're going to make an AI review. We need to make an immediate classification decision, which will say whether we will accept the post, so the post is going to remain on the platform, or we should reject the post, which means that the post needs to remove from it. Now, this decision needs to happen immediately, because even if we temporarily decide to remove, we need to make a decision about whether the post is going to be shown or removed. Kira.
Is this just your proposed algorithm, or is this comparing to what is done in practice?
So this is the high-level pipeline of what is the schedule of decisions. And in the paper, we discuss how it is described by a paper from Meta Platforms and how this connects. But essentially, when a post, this is my proposed formalization of how to think about it. But when a post comes, you actually need to decide whether it should be removed or remain, right? So what will exist on this platform is kind of like canonical, I would say. When I will go to the model, we are going to make some assumptions that are going to be specific, idiosyncratic for the results that I will say. Okay, so subsequently, after we make this decision about whether the post should stay on the platform or should be removed, we should also decide whether it should be sent on a queue based on which the posts are going to be sent to human reviewers. So this is an admission decision. And then we're going to decide whenever a human reviewer becomes available, we need to decide which of the posts is going to be scheduled to the human reviewers. And as I said before, there are two roles that human reviewers have. There is an enforcement role. Potentially, we are going to overturn the AI decision because the human reviewers will tell us so. And there is also a labeling role that will allow us to improve the future accuracy of AI.
Yes. It's not about the removed one, right? So you never send the removed post to the human.
You could, in principle, you could still send that, yeah, in principle, you could allow to send the removed posts as well, because maybe something is very highly
right? So otherwise, you're going to miss all the.
Yeah. So, but it could be that something, for example, is very dangerous to be even shown. So maybe you are going to temporarily keep it outside of the platform and then send it for human review until it is verified. So in principle, it can be both types of errors. So in learning theory, this kind of feedback structure, where you only receive label for a post that you have selected to send to human reviewers, is called selective sampling, because you select essentially to which posts you're going to sample essentially in order to get labels from. So again, the main question in this talk is how can we make classification, admission, and scheduling decisions in a way that combines the responsiveness of AI with the reliability of humans. Are there any questions on the high-level direction of what I'm trying to do?
What would be the objective?
Good. I will go to the objective. On a high level, the objective is to minimize the total harm that is done, essentially. And the harm could be either you remove good benign post or you're keeping on the platform malicious post. Yes.
You assume that humans don't make mistakes.
I will assume, until now, I haven't assumed anything. In my model, I will assume that humans are accurate. So, and this is a very interesting open direction of thinking about how to incorporate inaccuracy, imperfect information from humans. We will assume, though, that humans are going to have perfectly accurate decisions. Yes.
When it comes to improving the AI accuracy, are you hoping to minimize the number of human reviews required, or is that not?
No, what I'm hoping is that there is some uncertainty. So there are two natures of uncertainty. There's an epistemic uncertainty, which essentially relates to something that we can estimate from data, and that we will try to be able to improve. There's also an aleatoric uncertainty that relates to some uncertainty that is going to happen regardless, essentially, about what we're going to do. So we're going to try to be able to estimate the epistemic certainty in a way that also tries to deal, essentially, but also make decisions that take aleatoric uncertainty into account, essentially. Okay. Let me move let me move forward to describing the two heuristics that one can think of, and then I will define formally the model, and we can discuss more questions about the model afterwards. So there are two heuristics that you can think of. The easiest heuristic is to say, let's not use AI, let's go back to the beginning of the century and have an automation-free heuristic. Okay? Going back to the numbers that we saw from Facebook, we can clearly see that this is unrealistic. In concrete terms here, this would mean essentially that the queue is going to essentially overflow, and therefore you're going to have extreme delays in the system that only requires relies on queue. Now, the typical way that in most of these applications, essentially, you think about incorporating humans in the AI is by having the AI output a score on the harmfulness. Think of it as the probability that the post is bad. And then have two thresholds, a low threshold and a high threshold. If the score is below the low threshold, so if it's highly unlikely that it's going to be bad, then we're accepting that and we're not sending that to human reviewers. If the score is above the high threshold, then we are removing that and we're not sending that to human reviewers. If it lies between the two thresholds, then we're going to make an initial decision because we need to make an initial classification decision, but then we're going to also admit it for human review in order to improve this decision afterwards. So this is kind of described in empirical papers from Meta Platforms. These are very nice papers that essentially try to optimize the scheduling decisions, assuming that essentially you have this initial pre-processing component, and essentially try to make good scheduling decisions in order to decide what to send to human reviewers. So what are the challenges in this approach with the two thresholds, essentially? First of all, there is a lot of uncertainty that is coming that a post has. They refer to as aleatoric uncertainty or idiosyncratic uncertainty that cannot really be captured with a single scalar post score. For example, if you think about the word crazy, if you are using this word crazy to talk about the crazy accident, this is perfectly legitimate and perfectly fine. But if you're using the word crazy to describe a person, then probably this is not a very good a post that you would like to keep on the platform. So, and of course, you can have a more careful featureization, not having just single words, but in anything that you're going to do, you're going to still have some uncertainty that is going to remain. Now, the second thing, and this is a plot from the first paper from Meta Platforms, is that there is a lot of fluctuations on both the arrivals of the post and on the reviewing capacity, which means that if you have these two static thresholds, you will end up in a situation where you will either underutilize your human review system or you are going to overcongest it. So you need to actually also take that into account, essentially. And finally, there is an issue with representation bias, because if you have these two thresholds, you are only going to get labels for everything that lies between the two thresholds. You are not getting any information about posts that have scored higher than the high threshold or lower than the low threshold. So this essentially means that it will be difficult for us to keep our systems going. So let me describe the model, and that will allow us a formal model to allow us to capture what I'm discussing. We're going to assume that we have a finite number of types. I will discuss a contextual extension towards the end, but for the time being, there's a finite number of types, k types. And this type has a lifetime, which means essentially how many periods users are going to engage with this particular post. And also, each type has a particular processing rate. Think of it, for example, if the type is a video, then it will take longer for a reviewer to actually process the post than if it is a text, for example. And also, we're going to assume that this type has a cost distribution that I denote by Fk, and this is going to be unknown on the platform, so we will need to be learning that online. Now, at every period, a post arrives, and the post that arrives has an observable type that I denote by K of t, and they also have, and this type K of t will come from a potential time-varying arrival distribution that I denote by lambda of t. Now, the post also has a cost that stems from the distribution of the associated type. So the cost of the post is a random variable that is drawn from the distribution of the type. Now, how should you think of it? If the cost is negative, this means that actually the post is good. So we would like to keep it on the platform. A negative cost means that essentially there will be this utility by removing the post from the platform. If the cost is positive, this means that the post is bad, and we would like to remove it in the platform. If we keep it on the platform, we are going to actually incur harm. And we're also going to have a time-varying reviewing capacity that I denote by capital N of t. So this is all the notation I have essentially. So if there are any questions. So we are allowing, because to capture fluctuations, we are allowing both the relative probabilities and the reviewing capacity to be varying across time. Now, as we said before, we need to make a classification decision. So we need to decide immediately whether to accept or reject the post. And subsequently, we also need to decide whether to defer it to humans, so whether it should enter a queue. And when a reviewer becomes available, we need to decide which post to schedule to human reviewers. The human reviewer is going to finish the post with a time that depends on the processing rate of the type and the reviewing capacity at this particular time. And we're also, as we discussed before, we're also going to assume that they're going to observe correctly the exact cost Cj of t. So they are perfectly accurate in what they observe. And as I discussed before, there is an enforcement component because maybe we had kept the post on the platform and now we realize that the cost is positive. We can correct this decision, or maybe, or vice versa, essentially. So we can correct the decisions, essentially. And there's a labeling component because we can now observe the cost of this particular post, and potentially this can help us improve future decisions. And again, as I said, in learning theoretic terms, this is called selective sampling because you're only getting data label data for the post that you select to sample.
Are the lambda probability, like the probability of a post being a certain type, are they static over time or do they change?
It's time varying. So a lambda of t, that's why I have the t dependence as well. Yeah, it's time varying, and we don't assume that we need to know actually what is the arrival probabilities. Good. Other questions? Yes.
Do you assume your classification system to be fixed, or you're going to use that kind of false positive and false negative feedback from human to update your?
I'm going to use the labels that I'm getting in order to improve my system essentially. So initially, I don't have a good idea about what the different cost distributions are, but over time, essentially, I collect it. And it's an online learning perspective. So yes.
Is there any way that you capture like the cost of making a human review something, or is kind of like as long as you're within the capacity that they have, it's okay?
So there is the processing rate essentially says, so this mu k of t is how long will it take for this human to review. So essentially the cost essentially relates to the delay until it becomes available again, essentially. So it's a queuing cost essentially, because for as long as the human is working on a post, they cannot work on another post essentially. Good. Yes.
The thresholds, we're assuming that they're like fixed, or and they also like even like randomly select based on what was recorded.
Yeah. So the thresholds, the two threshold technique that they discussed was the heuristic. We're not going to rely on the thresholds that are fixed, and we'll discuss when I discuss our algorithm essentially what we're going to. Yes, one more question.
Once a post is in the queue, is it inflicted cost?
I will discuss, let me go to the objective to actually discuss exactly what's the cost that the post gets, because this gets to this point. So the cost that we will get from a particular post depends on two quantities. The first one is the cost for every period, and the second one is the number of periods that it's active. So what does the number of periods that's active mean? Active means that essentially it is on the platform. So in particular, if we make a classification decision to remove a post, and we also don't send it to human reviewers, the number of active periods is going to be equal to 0. If we make a classification decision to accept the post, and we don't send it to human reviewers, the number of active periods is going to be equal to the lifetime. If we make a classification decision to accept the post, and then we send it to human reviewer, the number of active periods will depend on the scheduling decision. So for the time, so to answer your question, essentially, the post is going to incur cost if it is accepted on the classification decision and it is in the queue, for as long as we correct the decision. So essentially, we're collecting cost for every time that the post is active. And the loss essentially that we're having essentially is the average cost of all the posts minus an omniscient optimum. The omniscient optimum has access to the exact cost, so it will remove the costs that have the posts that have positive cost, and will keep the posts that have negative cost. So it will take the minimum of 0 and the cost. Now, we are making the assumption that humans observe the actual cost, and only humans observe the cost. So one problem that you can see with this as benchmark is that actually it doesn't capture the limited human capacity. So we will need to actually, when we find regret, to evaluate how well we're doing, we need to compare against the benchmark that does capture the limited human capacity. And the simplest way to think of it is in a stationary case, the benchmark can only have access to the realized cost for a rate of posts that is equal to the reviewing capacity that you have at this particular period. And because we want to have non-stationarity, we use techniques from non-stationary learning queuing systems by Yang, Srikant, and King, and also Nguyen and Modiano to also allow for non-stationary settings. The idea is there that you can use reviewing capacity for nearby posts, essentially. But this is kind of like the high-level idea. So the benchmark can only have access to the realized cost for those many posts and can only work based on expectations for anything else. Now, what's our main result? Our main result is that we give a regret guarantee that scales as square root of the maximum lifetime and also has a term that vanishes as the time horizon goes to infinity. The square root dependence of maximum lifetime is tight. We have a lower bound that actually shows that you cannot improve that. And we also saw that the heuristics that I described above, like human only, AI only, and static thresholds are all going to give you linear regret with respect to the maximum lifetime. We also have a contextual extension that replaces the dependence, removes the dependence on the number of types. And this is the first result, to the best of our knowledge, for online learning in contextual queuing systems. So I think our techniques can be useful more broadly when you think about contextual queuing systems and learning. Any questions on that before I go to Shefahida?
So, let's say I could design N of T. Would I not put all my human capacity up front so that I can give a lot of good information to my AI model and when it correct it?
Right. So the simplest way to think about MT is like you have some number of people. So you cannot just multiply these people and put them all in the beginning, essentially, right? So
if I could kind of have train a perfect AI.
Sure. If you were able to have infinitely many human capacity, then you would not operate with limited human capacity. Yeah, you would be able to train that. Still, this would not be the optimal thing because there is enforcement reason as well. So maybe there is some aleatoric uncertainty that arises so you may want to use capacity in order to correct decisions that are happening from the AI. So there is the labeling component, and what you're describing is essentially going to solve the learning issue, but the labels are also used for enforcement in order to, maybe you made mistakes because of uncertainty that exists. Because for every type, we only know the cost distribution. So essentially, the realization we can only access through humans, essentially. But throughout the talk, I'm assuming that the human capacity is fixed, is exogenous, is not a decision variable, essentially. But yeah, yes.
I guess you're assuming that for the jobs that you decide, for the posts that you decide for the humans to review, you're delaying them and not showing them on the website. Would it be also helpful to say you can show them on the website, and then if humans thought it's not relevant, then drop it?
I'm allowing both. So if the classification decision is accepted, the post is shown on the website, and I'm potentially going to remove that afterwards. So it depends on the classification decision. If I classify it as accept, it will stay on the website until potentially being corrected. If I decide reject, it will not be shown on the website until potentially corrected. So what I want to describe is I want to describe the three main ideas that discuss on how results are generated. How much time do I have?
2:15.
Okay. So 20 minutes.
I mean, good question.
Yeah, good. Okay. Yeah. Okay. So there are three important components. The first one is we will start with assuming that we know the cost distributions, and we will highlight the first insight. Even if you know the cost distributions, how should you design actually the system? The second one will be about explore exploit. We do not know the cost distributions. We need to learn them online. How can we do that? And we will see actually that canonical approaches will fail in this case. And finally, we are going to see how we can extend it to contextual queuing systems and what enables us actually to get what I said, the first online learning algorithm for contextual queuing systems. So Let's start with a situation where you have a finite number of types, and for every type, we have a distribution from which the costs are coming. Okay, this is the FK that I discussed before. Remember that when we were discussing the heuristics, we were having the automation-free system was suffering with very huge delays. Remember this overflow that we were having of the queue. So essentially, you had a lot of congestion. On the other hand, you were having in the static two thresholds, you were suffering from the idiosyncratic uncertainty and also from non-stationarity. So our admission decision is going to be driven by these two observations, essentially. And what we'll try to understand is, what is the cost of not sending a post to human reviewer? So if you're not going to send a post to human reviewer, this means that you need to make a classification decision and never correct it. So if you're making this as classification decision and never correcting, to back to this point, you're going to suffer from the idiosyncratic error you have. The cost distribution would have some positive mass, some negative mass. You will suffer from one of the two. But you can actually estimate exactly what's there. You can estimate what's there on an accept decision. This means that you will keep it. So if it turns out that the cost was negative, that's great. But if the cost was positive, you're going to suffer that. So it's the expected positive cost, essentially. And in a similar way, you can estimate what is the cost of a reject decision. If you reject a post and it was positive, excellent. But if it was negative, you are actually going to suffer from that. So it's essentially the absolute value of the expected negative cost. So if we knew the cost distributions, we are in the world that we know the cost distributions for the time being, we can estimate those two costs. We will take the minimum of the two, and we're going to select the accept or reject decision that minimizes the cost we will have. And given that we're not going to send it to human reviewers, we're going to suffer this cost for all of the lifetime, because we will not be able to potentially correct that. Now, what is the cost of deferring the post? If we defer the post, really the cost that you're getting is coming from the congestion that you're causing to other posts. Because if I'm adding a post to the queue, then this means actually that other posts are going to take longer potentially until they are reviewed. Now, this can be captured. A proxy that you can use for that is the queue length of all the posts of the same type. And this is inspired by the drift plus penalty analysis that was introduced by Stoliar and popularized by Huang and Neely. And so this idea essentially says that you can use as a proxy for the cost of the congestion cost that the post poses, the queue length of the particular post of particular type. So what we're going to do is we're going to send a post to defer a post if and only if the cost of not doing so is higher than the cost of doing so. In game theoretic terms, the way that you should think of it is that you should try to understand what is the externality that this particular post is causing to the system, and you should send a post to the human reviewers only if it is worth essentially the externality that it causes to the human system. So I want to emphasize one thing about that unlike the two static thresholds that we were discussing before, this is a congestion-aware tool, because we can automatically adapt to fluctuations that are happening in arrival posts and reviewers. For example, if suddenly we adopt back the suggestion and we completely shrink our human capacity afterwards, the queues are going to increase, which means that the threshold to send a post to human reviewers is going to be significantly higher. So we can automatically kind of adapt to such fluctuations based on this particular rule. Now, with respect to the other two decisions, remember we have two more decisions. We have a classification decision that says that, which is easy here. We know exactly what is the error on accept, what's the error on reject. We will just select the classification decision that has the minimum of the two errors. And we also have a scheduling decision that we will adopt the classical max weight that essentially prioritizes posts that have longer queues, but also takes the processing rate into account. So this is the classical way to stabilize queuing systems, essentially. You select a post from a type based on this maximum weight. So that's the first idea. The first idea is that we need to use congestion-aware rules, and we need to take into consideration the queue length, essentially, the congestion in our system. And as we said, if you don't use congestion-aware rules, you're going to have linear regret, and you're going to suffer essentially from the problems that we were discussing. Let me go to the second idea. Now, we understood how to do things when we know the cost distributions. What if we go to learn them online? Suppose that you actually do not know the cost distributions. This means that you cannot really estimate what is the expected positive cost and what is the expected negative cost, because those depend on the cost distribution at K. So you do not really know what is the cost of not defining a post, because this depends on the minimum cost of error of accept and the minimum error of reject. You do not know these quantities if you do not know the cost distribution. Now, what is the typical approach? The typical approach is to do bundles with knapsacks or bundles with constraints, which this is a paradigm, for example, that was popularized by Steve Agrawal and Nikhil Devanur. So what's the idea? The idea is, okay, pretend that you knew this information that you don't know. So pretend that you knew error of accept and error of reject. Design an algorithm for this setting. Good news, we just did that. The previous thing that we did essentially was this BASID algorithm that balances the idiosyncrasy and the delay is exactly what we have done. So step one, we have already done. Great. Let's go to step two. So what's the step two? Step two is try to collect data over time and create sample averages about the quantities that you care about. So you create an empirical mean about what is the error of accept and the error of reject. So you take any data that you have and you do that. And then create optimistic estimates about this quantity, because this is not going to be completely accurate. So create an upper confidence bound that says that with high probability, the true mean is below this upper confidence bound. And you create that with some Hefting bound or Chernoff bound. So, and the idea afterwards is that once you have created these optimistic upper bounds, these upper confidence bounds, you just replace the quantity that you don't know with these upper confidence bounds, which you do know, because you just took an empirical mean, you add the confidence interval, so you know the upper confidence bound. That's a very canonical recipe to deal with bundles with constraints. The reason why it works well is because if you make a mistake, what will happen is that you may over-admit. So you may admit a post that you would not want to admit. But if you admit that post, you're actually going to get labeled. So you're going to actually shrink the confidence interval. So eventually, you're going to make admission decisions that are essentially as good as if the parameters are known. Because whenever you make an error, you refine your estimates, and eventually you're going to be very, very close to the means. So you're eventually going to be behaving as if you knew those distributions, if you make errors. Now, the problem that we're having in this case is that we don't only make the admission decision, we also have two more decisions. So the scheduling decision is fine, we're just using max weight, we're not relying on anything. But on the classification decision, we're actually accepting if the error of accept was smaller than the error of reject. The error of accept and the error of reject depend on information that we don't know, because they depend on this expected positive cost and the expected negative cost. So there is a question of how soon are we going to be able to understand what is the sign of that. If we know that the error of accept is larger than the error of reject, that's great, we're going to make the correct classification decision. So let's try to understand how soon we're going to be able to estimate. And let's assume that we have just two types. So you have one type that is arriving with probability 0.8 and one type that's arriving with probability 0.2. And the service rates are 0.5 for both. So it takes you, with probability half, you're going to be processed. Now the cost distributions are very simple. With probability 0.6, cost is 1. With probability 0.4, cost is -1. Now, given that, you will soon be able to, you should realize that essentially it's better if you were not, for the classification decision, it's better to remove the post, because the cost of the positive cost is going to be with probability 0.61 and will be -1 with probability 0.4. So in expectation, the cost is positive, so it's better to actually classify that as negative. And also let's assume that the lifetimes are 500 and 100 appropriately. Now, focusing on the first type, you soon see that actually if I plot the difference between the error of accept and the error of reject, this difference, and you plot the upper confidence bound and the lower confidence bound, the lower confidence bound actually becomes positive very, very soon. So given that the lower confidence bound becomes positive, we know that the error of accept is going to be larger than the error of reject, which means that we're going to actually go with rejecting, so we're going to remove the post, which is the correct decision. Now, with respect to the second type, though, you could see that if you use this optimism-based approach, the upper confidence bound and the lower confidence bounds actually stay static, which generally means that you actually don't get any data. But why does this happen? I just promised you that our admission is going to be as good as if we knew the parameters. So what is going wrong here? The problem is that if we knew the parameters, there is no reason to ever send a type 2 post to the reviewers, because the type 2 post is only going to stay for 100 periods. So if I knew the parameters, the correct admission decision for enforcement purposes, if you don't care about labeling, is always to send a type 1 post. So sure, UCB and optimist-based learning is going to do the correct thing if you knew the correct cost distributions, but the correct thing is not actually giving you labels in order to improve your system further. And the issue that we have is this selective sampling aspect, that the data that we're getting are not only useful for addition for the current post, but are also useful for future classification. And I think there's an interesting insight from that. We tend to think about UCB as explore-exploit, which is kind of an accidental byproduct to some extent, in the sense of like, really what UCB does is it creates an upper confidence bound on the quantity, so it's optimistic. But then it exploits based on this information. So it's kind of doing myopic exploitation for the current post. It's not forward-looking of trying to actually improve the information you have about your system in the future. So whenever you are using UCB in a system that also has downstream decisions that may be important, you may want to actually consider how you are going to collect labels in a more forward-looking way. So essentially what we're doing is that we need to combine the optimism and max weight with a more label-driven admission that will allow us to get the information that is important for future classification. Now, so the main result again is that we get a guarantee that has a square root of maximum lifetime plus a term that vanishes with the time horizon. As I said, the first insight was that we need a congestion-aware rule, even if you knew the cost distributions. It's important to balance the idiosyncrasy and the delay and to adapt to the fluctuations in the arrival post and the reviewing capacity. Again, the idea is that you think about for each post, what is the externality that will cause to the system, and you're only adding that to the review queue if it is worth the externality that it causes to the system. And the second idea is about learning. Really, it says that if you just use UCB, you are not going to get to act in a forward-looking way. And the data that you're getting is actually useful not only for the current post, but also for potentially future classification decisions. So you need to actually add label-driven admission. I have one slide, and as I said, this is tight, and typical heuristics are going to be have a regret that is linear to the maximum lifetime. Now, I have one slide board that I want to discuss that's about contextual case. Until now, we assume that we know the number of types. This is just K, and you can see that on the result. Now, if you think about how the types is coming, typically the type will be, you do a pre-processing on the metadata, on the unstructured metadata of the post, and you will get essentially type. The type could be a very big word embedding, for example, or contextual embedding, essentially. So it can be very large, the number of types. So we also have a contextual extension that it moves the dependence on types. And as said, this is the first result for online learning in contextual queuing system. Let me just briefly discuss the two ideas in order to do that. So the first place where we were using the fact that we have a finite number of types was when we were using this diffs plus penalty approach that was essentially saying that we will use as a proxy for the cost that the congestion that the post is going to cause to the system, we will use as a proxy the queue length of the associated type. So we need to keep a separate queue as a result for each type, which may end up leading to over-admission. The second challenge was that we were keeping an estimate for every single information, for every single error of accept and error of reject, essentially, which may mean that we will have over-exploration because we need to get data in order to fit all of these different buckets. So our first idea is that we're going to actually cluster types in groups based on the similar service rate. And the idea is that essentially the way that max weight works, really it only distinguishes things based on the service rate. So I think that this is actually an interesting idea that can be used more broadly in order to try to tackle contextual queuing systems. So try to group types based on the service rates, essentially. And the second idea about dealing with the overexploration issue, we use techniques from linear contextual bandits in order to transfer information between different types. The challenge that we have is that we need to deal with endogenous queuing delays. The queuing delays are endogenous to our decisions, so we need to actually do some work there. So the regret that we get in this way is that we're replacing the dependence on the number of types with a dependence on the number of groups. And also we have a term that vanishes over time. If you don't like having dependence on the number of groups and you prefer worst case guarantee, we also have a worst case guarantee that does not have any dependence on the number of groups, and it is scaling us a maximum lifetime to the 2/3. It's an interesting open question of whether you can actually do square root of the maximum lifetime in this case, but this does not have any dependence on the number of groups, essentially. So to wrap up, what we discussed today was we discussed about AI automation with limited human capacity. You have a system where you need to make classification decisions for all the posts, but you only have a limited human capacity. And the human capacity is used for enforcement, to improve, to correct current decisions, but also for labeling, which means that you will be able to make better decisions in the future. The first idea, we started as typical from in learning into complex systems, we started with a situation where you knew the cost distributions, and we saw that actually you need to have congestion-aware admission rules that try to balance idiosyncrasy and delay cost, and also are trying to are adapting to the fluctuations in the arrival post and the reviewing capacity. Then we proceeded to learning. We saw that UCB is actually optimistically myopic. It only thinks about the current post, but it's optimistic in the way that it thinks about it. And it is not forward-looking in its nature. So whenever you have a decision where the data that you're going to collect today are not only useful for the current post, but have a potential downstream effect on other posts, you may want to actually consider about how you're going to do label collection in a more forward-looking way. And this is an issue that we're encountering here. And finally, we need to handle the over-admission and the over-exploration that happens when you have a lot of types. And the two ideas is that we will group types based on the service rates. And the second one is that we will transfer information across different types. So with that, I would like to thank you. I'm happy to answer.
We have time for one question, maybe.
There are.
I'm wondering if you thought at all about how to model potentially harm to human reviewers from viewing disturbing content.
Yeah, we're actually thinking about that these days. We're not modeling it here. Like one way that you can view that is that could affect the future processing rate they have, or potentially even they may leave the system. So we're actually playing now with ideas about how to actually model this effect essentially on human reviewers, and yeah, generalize these things. So stay tuned, but I'm happy to discuss more.
Thank you.
You want to take one more?
Sure, quick up. Okay.
You pick one.
Okay, Hans, you haven't spoken, I think, yeah.
Yeah, so the arrival rate is that you allow time varying arrival rates, but the regret bound does not have to depend on how the arrival rate changes, of course.
Yeah, I'm assuming that at every period there is just one post. So you have the number of periods is the number of posts, but the arrival rate, what I say that time varying is that the distribution of types at a particular time can be completely different. Essentially, like it could be that in the time 1, essentially type 3 is going to come with probability 1, while in this next period type 4 is going to come with probability 0.5. So the distribution of which post is going to come in a particular round can be varying across time, but we are assuming that we're going to have essentially one post that arrives.